Hello, hello. Hello, hello, hello.
It will be detected. Okay. No pocket.
Just keep-
Down pocket is the because on the camera it will be.
I see. Turn on one AC maybe. One is on. Right? Yeah, right one is on.
Yes.
I see them. I see they are from my.
Once you can check this, like changing is happening on.
Yeah, yeah. Is Shuvrat coming? Shuvrat coming? I see. Hey, Shuvrat Raju, of course. I guess the new graduates are probably going to take a break from the seminars.
Hello, everyone. We have Aditya Jain from Ashoka University today. He will talk about invariants and correlators in 4D superconformal field theories.
All right. Thank you very much for having me. I'm from Ashoka University. I work with my thesis advisor or my PhD advisor, Amin Nizami. And today I'll be talking about some work that we did in 4D superconformal theories. Right. So let's get into it. The primary aim of our work was to determine the general form of any 3-point correlation function in a 4D n equals to 1 superconformal theory kinematically. So we know that that superconformal symmetry is enough to constrain 2-point and 3-point correlation functions. So we want to figure out all the correlation functions of, or we want to see how much superconformal symmetry actually fixes the correlator up to. All right. So to do this, what we did was we first formalized the 4D CFT analysis. So we first looked at the 4D conformal symmetry, and we saw how conformal symmetry constrains the theory and constrains the correlation functions, the 3-point correlation functions. And we do so by constructing these so-called conformal invariants. So again, this goes back to more than a decade back, where Giombi, Prakash, and Yin actually did this work of constructing all an exhaustive list of conformally invariant structures made out of 3 coordinate space points. And using them, they can be used to express any general 3-point correlation function. It doesn't have to be conserved current also. It can be any 3-point correlator of any operator, primary operators, of course. Now, once we can do this, we can calibrate and repeat this process. We can augment this process for a superconformal theory, and we can figure out superconformal invariants and express superconformal 3-point correlation functions of, again, a general arbitrary superfield operators. Okay, so looks quite straightforward. It's not quite straightforward. There were some subtleties in it, and we'll get into this. Right, so first let's look at the CFT the conformal theory. Again, this is the 2011 Geombi Prakashian's work. They worked in 3D CFTs, and we have extended to 4 dimensions. Of course, all of this stuff has been done in the literature, in the conformal theory. The superconformal theory is where the novel stuff comes in. But for the sake of setting the methods and formalism right, I'm going to show you what the 4D CFT analysis looks like. So what we do is we use auxiliary spinors, right? They're built out of, just like the auxiliary polarization vectors, we can use auxiliary spinors and the transformations under conformal inversion to construct an exhaustive list of invariant structures out of 3 points. Okay. Once we can do that, once we have written down an exhaustive list of 3-point invariant structures, we can write down any 3-point correlator using those invariants, using multinomials or polynomials of those invariants. And since we can do that, we can also impose conservation on each of the operator in the 3-point correlator, thus giving us correlators of conserved currents. Okay, so let's see. Right, so in 4 dimensions, or actually in any dimension, conformal symmetry is actually Poincare symmetry, dilatation symmetry, and special conformal symmetry. And in 4D, Lorentz group is SL2C, is isomorphic to SL2C. So what we're going to do is we are going to consider representations of SL2C, which are going to be labeled by 2 numbers, I, j. So, for example, a spin 1 would be given by a representation half, half, and so on. So what we do is we only look at spin S or integer spin operators, which are going to be representations S over 2, S over 2. And these are going to be symmetric traceless. All right. Right. So once we do this, now what we do is we use polarization spinors. Okay. These are used twice. Once they're going to be used to augment the coordinate space. So the coordinate space in 4D is x mu. And now we also include lambdas, the lambdas and the lambda bars. There's going to be lambda and lambda bar because of the SL2R thing in SL2C. And what we now do is use these lambdas and lambda bars to write a general spin-S operator in an index-free form. How do we do that? Let's say we have a spin-S operator with mu vector indices, with S vector indices. I contract all the mu's with sigmas, and now we have a 2S multi-spinor kind of an object. And now I can contract all of these spinor indices using lambdas and lambda bars. Okay, and hence what I get is an index-free operator. Of course, it acts like a scalar, but it's still spinning in the sense the spin information is encoded in the number of lambdas which are contracted. All right. So once we have done this, now we can write down any operator in the form of an index-free operator. Yes, please.
You said you are focusing on symmetric traceless operators.
Yes.
But you said that in the literature, these things have been worked out. But in the literature, have people worked out for arbitrary spin or arbitrary I and J?
I think there was some recent work on arbitrary spins as well, but the literature actually works with, the literature actually works with the polarization vectors, which only tackle symmetric traceless.
The final answer for arbitrary I1, J1, I2, J2, I3, J3.
I'm not sure, but I'm not sure if it's completely worked out for every general spin. I'm not sure about that. That's a good question. Right. So for the symmetric traceless case only, we're going to be working. Right. So how do we construct the invariant structures, the conformally invariant structures? Right. So Poincare invariance and dilatation or scale symmetry is easy to implement. What's hard to implement is the special conformal transformation or the special conformal symmetry. But what we're going to do is we're going to use this special conformal transformation written as a composition of inversion, translation, and inversion. So we can use the properties of inversion to figure out conformally invariant structures. And this is, of course, the form of inversion. X mu goes to x. It's basically 1 over x mu. So written in a covariant form, this is x mu going to x mu over x squared. So what are conformal invariants then? Conformal invariants are structures which are Poincare invariant, which are scale invariant, meaning they have 0 scaling weight, and which are inversion invariant up to a sign and conjugation. Now, this is important. So these are all the structures that we can build. This is an exhaustive list, by the way. So I'll explain what's up. So these x's are actually so small x's would have vector indices. You can contract it with, or you can multiply it with the sigmas to make them into bispinors. So these X and X tildes are bispinor matrices built out of X, the coordinates X. And these bispinors are now contracted with lambdas and lambda bars, which are now part of the coordinate space. And now this thing, it is clearly Poincare invariant because there are no outright Lorentz indices.
X1 to -1, you mean inversion of X1?
No, yeah, that's a good point. And I should make some formalism clear. Where's the chalk? So X mu goes to X, let's say alpha dot. Okay. Is this? Should I write a bigger? Okay. So right, and we can have X inverse. Okay. So if we have X, we can also write down X tilde, which would be, alpha dot alpha kind of a thing. And if I contract these two, I can write down this as X squared delta alpha beta kind of a thing. So this would be, say, this something like this, and then alpha dot beta. Yeah.
X tilde is the inversion.
No, there's no inversion right now. Yeah, this is just sigma tilde. So if you write down this is just a scalar quantity, and now you can use this to bring this to the other side, and this will give us the X inverse. It can give us both the inverses of these. Does that make sense? Okay. So X tilde contains, in SL2C, you have two copies of this invariant tensor. You have sigma and a sigma tilde or a bar, yeah. So X would, so X, there we go. X contains sigma and X tilde contains sigma tilde. So it's kind of a, there's a subspace thing happening in for SL.
Inverse in the alpha beta is.
Yes, that is right. Perfect.
As a matrix in the
Absolutely, yes. Right. So lambdas and lambda bars. Okay. So the thing is, let's say you have a spin S operator. Let's say you have a spin 1 operator, right? I have a O mu. If I write down a 3-point function for this, let's say mu1, mu2, mu3, right? This would be conformally covariant. It would have some tensor structures, which would be, mu1, mu2, mu3, something like this, right? As I move up the spin in this, I'll introduce more vectored indices. The tensor structures would keep on increasing, it would keep on getting more and more harder to extract. So now what we can do, using these lambdas, everything is now a scalar on the left-hand side. And now I can figure out an exhaustive list of structures that can come up out on the right-hand side, on this side, since everything is a scalar. And I can just use multiples of them. Okay, so once we do that, we can write down any 3-point function. So that's what's happening. And these are the invariants. Can we switch up the lights if possible? Sorry. Yes, right. So that's what we do. So these objects are conformally invariant. How are they conformally invariant? These are Poincare invariant, clearly. Lorentz and translational, as you can see, they're built of x1, 2, so x1 minus x2. So they are translation invariants. They have 0 scaling weight, so this is an x inverse, and lambdas actually scale as x to the half. So these are also zeros. These are also scale invariant. And under inversion, these have a special property. Under inversion, x goes to x inverse. So this whole thing actually under inversion, I'll just write it down. Under inversion, p12 goes to minus p21. I mean, clearly you can see this is not invariant under inversion. This object is not invariant under inversion, but that's not a problem because we can have inversion invariance up to a conjugation. Because in the SCT, in the special conformal transformation, I have 2 copies of inversion. So I invert this, I translate this is translation invariant, so it does not change. And then I invert it again, it goes back to p12. So this is in full glory. This is actually, these are 5 permutations of these as well. So it'll be p12, p23, p31, and all of that. The 1 and 2 are space-time indices or space-time labels. Similarly, we can make the S13s. So what now we can do is, if you can see, we have lambda and lambda bars on the ends, and we can have strings of x's. Since they are bispinors, I can contract and keep on having strings of x's, right? So you have 2 of these, and in this you have 3 of these, and they're appropriately made so that their inversion gives you the same quantity. Their inversion, they are invariant under inversion up to a sign in conjugation. Okay, so we have P12, we have S13, we have S bar 13, and Q1. So P12 under inversion goes as this. S13 under inversion actually goes to its conjugate, which is this. And S13 bar under inversion goes back to one S13. So
Does lambda transform under?
it does. So lambda does transform under inversion. So lambda alpha would go as lambda bar alpha dot, and then some x inverse alpha dot alpha, something like this, maybe like this and then this. So the indices should be the same, right? So you can also see that lambda under inversion goes to its conjugate. Everything goes to its conjugate. Okay, Q1 actually is inversion invariant in all its sense because it contains lambda 1 and lambda 1 bar. So under inversion, it goes to itself. P12 goes to its conjugate, which is P21, which contains a lambda 1 bar and a lambda 2. So, right. So these are all the invariants in the conformal theory. These are 3-point invariants in the conformal theory. Now, what we do is we will only consider, for now, we're considering bosonic symmetric integer spin operators. Okay. If that is the case, they would be, when they are contracted with lambdas, they would have equal number of lambdas and lambda bars for integer spin, for bosonic, for traceless symmetric operators, integer spin, they would contract with equal numbers of lambdas and lambda bars. And if that is the case, I can actually not work with conjugation. I cannot have things which under inversion go to their conjugates. I'll have to have inversion invariant only up to a sign. I'll have to drop the conjugation part. For that, it's easy to do this because we can just multiply them with their conjugates.
I should think of these bosonic symmetric integer spin operators as having this Lorentz vector indices.
Yes.
And those are just two, a left-wise spinor and a right-wise spinor indices which have a lambda and a lambda bar.
That is right. That is right.
So this S and S bar are like not valid now.
S and S bar would not be valid independently, but if I consider, let's say, S times S bar, it goes to itself, right? It doesn't go to its conjugate, it is its conjugate. Similarly, P12 would need to be multiplied with its conjugate, which is P21. Q1 actually is okay because it goes to itself under inversion. Lambda 1 bar, that is right. So we get these structures. So Qi stays. We cannot have P12 or Pij, so we'll make this P hat ij, which is basically multiplied with its conjugate, which is equal to Pgi, of course. And again, the same thing for the S's. And these are two new things that we can also make from the P's. So if you consider this kind of a combination, it goes to itself with a plus sign. If you consider this combination, it goes to itself with a minus sign. Now, what's interesting in 4D inversion transformation is it also gives us parity. It also gives us the transformation under parity. So what we have actually figured out are, or what we're actually seeing are conformal invariant structures which are also even or odd under parity. So all these structures, from the first 4 ones, are actually even under parity because they go to themselves under inversion. The last one goes to minus of itself under inversion. It's actually odd under parity. So that would actually result in, let's say, parity-violating structures in the correlator. Again, the whole point of doing this is to figure out, or is to write down the expression for correlation functions. And these parity-odd invariants would amount to parity-violating contributions to the correlation function. Okay? Right. Also, what we see is that S hat and this P123 minus, these two are not independent. If you look at their structures, if you open them up, you will find that they're actually made up of Q and P's. You can actually write down a combination of Q's and P's, which gives you S and P's, this new one. And so, basically means they're not independent and we can drop them. And hence, finally, we have these 3-point conformal invariants. So they're conformal invariants and they're inversion invariants as well. The P hats and the QI are parity even, and the P123 plus is a parity odd one. These are all the invariants, and again, these have been done in the literature, but they are of course using different techniques. They have been figured out. There are 6 structures here, and there's a single structure here. Okay, and now how do we use them? Right. So I write down a general spinning 3-point function. Okay, general 3-point function, which is now written in terms of the index-free operators only. This is a scaling factor so that they scale correctly. And this, in the brackets, we have all the structures which are conformally invariant. Okay, and so now I can just look at the lambda structures or the spin structure on the left-hand side, and I have these which also have their lambda structures on the right-hand side, and I can just match the lambda structures, and that's going to give me all the contributions to the correlator, conformally invariant contributions to the correlator. For example, let's consider this correlator. This is a spin 2, spin 1, spin 1 correlator. The even structures that can come about in this are these. These are made up of the Q's and the P's that we saw in the last slide. There's also a single structure that can come about in the odd part. So this is an odd structure, a parity odd structure. It contains the P123 plus. Right, but these are all the structures that can come that are conformally invariant and which correspond to this spin. What's it called? A spin structure. Okay, but there's also one more constraint to the correlator, and that is there is a permutation symmetry of the second and the third operator. So if I exchange the second and the third spin 1 operator, I should get the same correlator. And hence, what we can do is we can look at how the invariant structures also change. So using the point suit symmetry of 2 and 3, since my invariants are also made up of coordinate space points, I can see what happens when 2 and 3 are exchanged. What happens is in the other structures, everything is fine. In these 2 structures, we can only use a linear combination, which is something like this, as you can see. Okay, and the odd structure cannot respect or preserve the symmetry under a 2-3 swap. So that has to be dropped. Finally, what we have is just for this correlation function, the form of the correlator is actually fixed up to 4 coefficients. Okay, and now you can do this exercise for as many spins as you want, because you just have to figure out what the structures are built out of our conformal invariants. And once you do that, you can have as many correlation functions as you want in the conformal case. Okay. Similarly, just a tag along with this, we can also have conserved currents in our correlator, and to do that, we just apply this differential equation onto the correlator. Okay, but this differential equation works when the current is written in its covariant form. If I have the current written in its index-free form, this is what this equation turns into. Okay, so now I can this is a differential operator. I can apply this differential operator on each of these points, and it will also constrain my correlation function, and it will give me the form of the correlator. Okay, but I'm not giving you any examples because this was a setup for the super conformal case, which we'll go to now. Right. So what's the idea for the super conformal theory? Again, we'll use the same kind of a formalism. We'll use lambdas and lambda bars to make the operators index free. Instead of inversion, now we use the supersymmetric counterpart of inversion, which is superinversion for the lack of a better name, of course. And we use superspace methods instead of coordinate space methods to now build super conformal covariant and finally super conformal invariant structures out of 3 superspace points. Okay, what we actually found, this was a head scratcher for us. What we actually found was the construction strategy that we used for the conformal case was incomplete to figure out these super conformal invariants, and what we had to resort to were the CFT invariants and relations between those invariants to figure out the full list, the full exhaustive list for the super conformal case. Once we have the super conformal invariants, we can write down all the correlators, 3-point correlators of any operator, superfield operator, of course. And then the same thing that we did in the conformal case, we can apply the conservation condition and write down correlation functions of supercurrents. Okay, so let's see how we do that. So superspace contains x mu, theta and theta bar. This is just a normal standard superspace variables. We decompose to chiral and antichiral coordinates. So we decompose these variables into chiral and antichiral. So we make this. Yes, please.
Earlier when we had this lambda and lambda bar, weren't those the super coordinates?
No. Okay, good point. The coordinate space in the conformal theory was x mu. That's it. And then lambdas were used to, write everything down in terms of index-free form.
I would think that, I mean, maybe
We'll still use lambda. We'll use lambdas with the thetas as well. So the thetas are now Grassmann odd. So they're anti-commuting Grassmann variables, which is part of the superspace. Okay, lambdas are bosonic and they're commuting. Okay, and they are just bookkeeping devices for the spin structure actually. All right, thetas are of course the Grassmann part of the super symmetric theories. Right, so we use this combination to write down the chiral and antichiral coordinates, and we only use spinor matrices. Right, so we'll not be working with vector indices at all. We'll change everything to spinor indices, and of course, again, the tildes are these which contain the sigma tildes, and the untildes one are the one that contains the sigmas. And so we have, using these, we can write down these two. And since I can already create a scalar out of them, I can also exactly like this. Where is it? Exactly like this, I can also create the inverses. Okay. So these chiral and antichiral coordinates are actually such that they're killed or they're annihilated by the chiral or antichiral and chiral super covariant derivatives. Okay. Now we have to construct the invariants, and how do we do that? We look at, again, we use the same construction strategy. We looked at, okay, in the conformal case, we looked at Poincare invariant objects and scale invariant objects which transformed under inversion, right? Now we look at super Poincare objects from 2 and 3 points. Okay, so this is an important object actually. This is a very important object. This is a super Poincare covariant object. It's made up of x pluses and x minuses and the thetas. And it's actually anti-chiral in I and chiral in J. So I and J are superspace points. So for example, I have an x 1 bar 2. So that would be anti-chiral in 1 and chiral in 2. And these are super translation invariant. So if you write down the super translation or the supersymmetry generators, acting on them, that would kill it. The Q would kill the I bar, and the Q bar would kill the J. Okay. Right. So using this, we can of course define the raised and the lowered indices and the inverses as well, just like the case of these and the x plus minuses. And so finally, we just have these 2-point blocks, and they're going to be really important because they are going to be useful in constructing the invariant structures by using a string of them. Okay. Now, so we also can build these 3-point objects. So in the last case, in the 2-point blocks, what we saw they were built out of 2 superspace points. We can also have objects which are built out of 3 superspace points. So as you can see, these are built out of 3 superspace points. And of course, they're also super Poincare covariant. Okay, and their permutations, of course. And what's new in the superconformal case is now we can also have Grassmann valued 3-point objects which are super Poincare covariant. Okay, so they would be transforming homogeneously under infinitesimal superconformal transformations. And of course these have been made like in the late 90s, more than or like quarter century back. These are made by Park and Osborne. So these are Grassmann valued. They're built out of these theta bars. Okay, they're anti-commuting, but they're still super Poincare covariant. And in the conformal case, so these are not present in the conformal case. These are These are Grassmann valued, which means if I remove the thetas, superspace variables, these just vanish. So these do not have a counterpart in the non-supersymmetric case. Okay. So these are all the building blocks that I have. I have the 2-point blocks. I have the 3-point blocks. Sorry, the colors are for some reason not showing up on the projector. These are 2-point blocks. These are 3-point bosonic blocks. Of course, these are built out of the 2-point blocks, and they have conformal counterparts. So these, if you remove the thetas, these would still not be 0. And of course, I have the 3-point Grassmannian blocks. These would be 0 if I remove the thetas, the small thetas. And of course, I'll be working with the auxiliary spinors, the lambdas and the lambda bars. Okay. So now I need to make superconformal invariants using them. How do we do that? Again, superconformal invariants can be written as super Poincare invariants plus scale invariants plus R symmetry invariants, which is new now, and special superconformal invariants. Now, special superconformal invariants, of course, is hard to implement, and what we do is we use superinversion. It's the same as the conformal, just as special conformal inversion or special conformal transformation can be written as inversion, translation, inversion. Special superconformal invariants can be written as superinversion, super translation, superinversion. So I use the same property, and since I'll be looking at correlators of symmetric traceless operators only, I will have superinversion invariance up to a sign only. Okay, no conjugation. And again, the same formalism applies. The plus and the minus under superinversion actually gives us the parity behavior as well. So I will have objects which have a specific parity behavior, which would give us parity even and parity odd contributions to the correlation function. Right. So what is superinversion actually? Superinversion is this supersymmetric counterpart of inversion. It takes the chiral, so x plus minus goes to x minus plus. So it's exactly the same as, not written it down here, as the conformal inversion, but now supersymmetric. Okay. And since theta is also a supersymmetric variable, theta goes to theta bar with some factors of x, of course. Okay. Again, these are all the vector indices and the spinor indices. I can write them down in the bi-spinor indices form. So x plus minuses, which were built out of these and sigmas, goes to x minus plus. So you can see the chiral goes to anti-chiral and vice versa. The 2-point blocks were built out of anti-chiral and chiral indices or points. So as you can see, xi bar j goes to xij bar under superinversion. And what we also have are these pre-factors and the post factors. So basically, this block transforms homogeneously, right? And now what you can also see is the 3-point Grassmannian block transforms homogeneously as well. Again, up to a conjugation. As you can see, theta goes to theta bar. Okay. It's not working for some reason. Okay. Similarly, the auxiliary spinor under superinversion goes to lambda goes to lambda bar. Okay. So now what we can do is, if you can see, lambda has this homogeneous factor of x inverse minus, and this thing, this xi bar j, has a homogeneous factor of xi plus inverse. So what I can do is, if I consider, oh, this is really not working now. Is there another? Yep. Yep. Battery is dying. Nope. It's fine. I'll just use this. Should I use the cursor?
Also, not also point with your hand.
Yeah.
Do you have batteries? Oh, perfect. Right. But maybe I can still talk. What we can see is lambda. If I take the lambda with the xi bar j's, I can see a combination of these two. I can remove the x factor under superinversion if I multiply them together. And similarly, perfect, thank you so much. So this factor can multiply with this factor and remove it under superinversion. Similarly, on the other side, I can also have a lambda which takes care of this factor. And so basically I can have objects which transform to themselves without these pesky factors, right? So that's basically what we do. We take lambdas or thetas. By the way, theta also goes as this, as you can see, it goes as homogeneously under superinversion. And if you actually squint your eyes, you'll also see a V1 here. This V1 is actually present because the thetas that we have constructed are charged under R symmetry. And so this is the manifestation of the R symmetry charge. The R symmetry charged objects under superinversion, the R symmetry shows up there. So this is what the V1 is. But of course, since we're working with new R symmetry neutral operators, we'll have to remove these V1s out of our invariants. Okay. So this is how we make the covariant structures. So I have, so this is a strategy for construction of these objects. I end or I close these things with lambdas or thetas because they have a single alpha or an alpha dot on them. And in the middle, I string multiple x's or these 2-point blocks. Okay. And I do this appropriately so that after superinversion, all these factors are removed. All these factors are cancelled by each other. Okay. So for example, I'll take 1 bar 2, which would give me a 2 minus here. And on the other one, if I take a 2 bar 3, it would cancel with this one. So the x factors would cancel out. So I can do this and I build all the objects that I can build here. I construct all the objects that I can construct with this strategy. And the issue with that is, one thing, it transforms homogeneously to m bar. So this object would go to its conjugate under superinversion. The lambda under superinversion goes to lambda bar, and yeah. So the whole object under superinversion would go to its conjugate. Right. So the 2-point blocks, I'm using the 2-point blocks products, but clearly the 3-point blocks which I defined here are made up of 2-point blocks as well. So that also are included in this. And it's a highly redundant construction. So what happens is you write down all the structures, which is a lot, by the way. And what you see are those structures are related to each other. If you open them up, if you look at their structure, at their component structures, they're all related. So what we need to do is we need to find a minimal or an independent exhaustive list. Okay. Also, what we have, if the structure contains a theta anywhere, here or here, it's completely Grassmannian, which means when I remove the small thetas, when I look at the conformal part, this structure is 0. That means it's a purely superconformal construction. It does not have a conformal counterpart. Okay. And now these transform homogeneous to m bar, right? So these go to their conjugates. But we require products of n's. So we will multiply them with themselves so that we have superinversion invariants, right? We cannot have conjugates since we need to write down correlators of symmetric traceless operators only. Okay. For example, I'll give an example of this. Let's say I have theta 1 contracted with itself, right? Under superinversion, this goes as this. It goes as minus this x1 minus squared, this v1 squared, which is a manifestation of the R symmetry, and psi 1 bar. So psi 1 goes to psi 1 bar, which is made out of theta bars. Okay. So psi 1 clearly goes to its conjugate with some v's. Similarly, if you remember the conformal case, we had made P12, the Pij. The Pij were built out of lambda 1 and then x and then lambda 2 bar, which is exactly the case here. Under superinversion, this goes to minus P21, which is what I wrote as well. Okay. So these are basically the supersymmetric extensions of the conformal invariants. Okay. So I listed down just 3 of them, but using this strategy, you can write down a lot, probably like 50 or something. But what we need to do is we need to make an independent set. Okay. So how do we make invariants out of them? Well, easy. We multiply them with each other. So psi1 multiplied with psi1 bar, and we do this division by some factor. I'm not going to go into the detail of this factor. It takes care of these x1 factors. Okay, but the point is psi bar under superinversion goes to itself, psi bar only. Similarly, p12 we do the same thing as we did for the conformal case. We multiply it with its conjugate p21, and under inversion, under superinversion, p12 hat goes to p12 hat. p12 hat is literally the supersymmetric extension of the p12 hat we built in the conformal case. Okay, now I'm going to give you all the invariants that we have in the superconformal case. Of course, these are not going to make sense, but I'm just going to give you the final names of them. So as you might remember, these are actually the same that we saw in the conformal case. These three. These are the independent ones, but there's still a subtlety left, and I'll get to it. But these are the conformal ones, right? Of course, these are the supersymmetric extensions of the conformal ones. Similarly, we also built S hats, and yeah, what else did we make? We had a Q, right? But now we can make Q1, Qi plus and Q1 minus, or Qi minus. Basically, what happens in the superconformal case, Q and Q bar was the same structure in the conformal case. In the superconformal case, this is the Q structure. This actually is a purely Grassmannian structure, Q1 minus or Qi minus, and incidentally, it's also parity odd. Okay, again, so these structures are parity even and parity odd by construction as well. So under inversion or superinversion, they would go to pluses or minuses of themselves, and that gives us the parity behavior of them as well. These are some others as well that we made or we could make. And these are an independent set, meaning these cannot be written down in terms of anything else, right? Okay, so these are the bosonic ones and these are the Grassmannian ones. The bosonic ones are called bosonic because when I remove the thetas, or when I remove the Grassmann odd things, these would go back to their conformal invariant structures. The Grassmannian ones are new here because the Grassmannian ones, if I remove the thetas, they just go to zero. They just vanish. Okay. And if you remember, I showed you this. So these are the conformal ones. The conformal ones were Qi, P hat ij's, S hat ij, P123 minus and P123 plus, where only one of them was odd. And then I said that the S hat ij's and the P123 minuses are not independent. There's a linear relation between them and the Q's and P's. So, oops, to press this somehow. Yeah. So these are the super conformal invariants now. Okay. So the Qi pluses are actually the Qi conformal ones, supersymmetric extension, and so are the Pi's, Pij's hats, Sij hats, P123 minus, P123 plus. And now we did not have this structure Y123 minus, and I'll get to it why we do not have it. And okay, let's see. So these are an independent set right now. And of course, the Grassmannian ones vanish in the non-supersymmetric case. But turns out there are more fundamental invariants that can be made, a couple of them. Okay, let's see how. Okay, to understand that, we have to go back to our CFT analysis. How come? Let's say I take a combination of bosonic invariants which are related in the conformal case. So if this combination, when I look at the conformal case, this gives me a 0. If that is the case, then that means if I do not take the non-supersymmetric part, if I do not take thetas to be 0, then this should be equal to a Grassmannian superconformal structure. Right? Does that make sense? It should be equal to a Grassmannian structure. And so that should hold for all the bosonic invariants. Okay. For example, let's consider this equation. So this equation is actually the equation which removed S hats from the conformal case. So in the conformal case, this is 0. This equation is true, which means S hats can be written as P hats and Qis and Qj's. In the superconformal case, on the right hand side, I'll have a completely Grassmannian structure, right? Turns out I do not have any invariant that I made which can fix this on the right hand side, a Grassmannian structure, which means this actually defines for me a new Grassmannian structure. This whole thing is now a Grassmannian structure because in the conformal case, it goes to 0. Right. This one or this one?
The one that had that next one, this one.
Huh.
Are you saying in the first line that the sum over conformal invariant is 0?
No, no, no.
That's just an identity.
Some combination. So that's some combination A.
Then what are you saying? Then
If there's a combination of conformal invariants which are related, then that means their supersymmetric extensions in the non-supersymmetric version are 0 as well, right? So I can write this as bosonic superconformal invariants, the same ones.
what do you mean on the right hand side of the second equation by Grassmannian? You mean it will start with 2 thetas.
It will start with 2 there. Yeah, you're right. Absolutely.
Still Grassmann even.
It's Grassmann even.
Nilpotent. What's called nilpotent?
It
starts with 2 theta.
It starts with 2 theta, yes. It's Grassmann E1, yes. But it vanishes in the non-supersymmetric case. Okay? Does that make sense? No?
Those are called nilpotent bosonic.
I see. I see.
So when you square it, it will be automatic. Or at least if there was a single theta when you square
Sure, sure. But these would not be 0 if you square them. Not all of them.
If you raise it to certain power.
Sure. Huh.
Enough high power.
Sure. Which is going to be true for every theta in the supersymmetric. Right. Sorry?
Yeah. But nilpotent, right? That's the correct word.
Not nilpotent, yeah, but it is soul out. Yeah, okay. So
I see.
Grasping not part. Only soul, there's never body.
2 theta, 4 theta.
Yeah, 1 theta. These are things where you say theta 0.
Right.
I think in some of Witten's papers or reviews of superfield theory, he uses the term nilpotent. Maybe that's something else.
Yeah, some of words similar.
Similar, I mean, if you raise it, as you said, if you raise it
Right.
to one number of power.
Yeah, that's true. So these are now Grassmannian invariants. These are of course Grassmannian even invariants, but these would vanish in the conformal case. And so this is one invariant that we could not make through our construction strategy. Similarly, so now this is why we did not consider the Y123 in the conformal case, because it's the same structure as P123 up to a sign, of course. So this equation means that in the conformal case, the structure Y123 is the same or is equal to minus of P123 minus, which is why we never considered it in the first place. In the superconformal case, these two are different structures and they differ by a Grassmannian structure. Okay, and again, there's no invariant that we have constructed which can fix that Grassmannian part. And so we have to call this a new Grassmannian superconformal structure. Okay. Lastly, this is the equation which actually removed P123 minus. So we saw that S hats were removed in the conformal case and P123 minuses were removed in the conformal case. This is the equation that removed it. And so let's look at the superconformal counterpart or supersymmetric counterpart. Turns out it's actually completely fixed by the new invariants, which are the R hats and the R13. So the invariants that we made here actually are used to fix this equation, which means now we can say with some confidence that we have a complete exhaustive list of invariants, which are these. So we have the bosonic parity-even invariants, which are exactly the conformal ones. Even the parity odd is the conformal one. And now we have these Grassmannian invariants for the superconformal case. So these would start with the theta theta bars, of course. And
would you find whether even in the superconformal case, are your superconformal primaries also traceless?
yes, they're traceless symmetric. Yes. Yes, that is right. That is exactly what we have. Okay. But that also covers like a whole lot of ground because the supercurrents and the stress energy and tensors as well. Right. So these are the Grassmannian invariants which are new for the superconformal case, and this is an exhaustive and independent list. And now we can just take multiples of them with the restriction that the Grassmann odd, so these ones, or actually the Grassmann invariants and the parity odd invariants, they can only occur linearly. Okay, while these ones, they can occur at any level or any power. Right. So with these at our disposal, now we can write down any 3-point function. Okay. So we consider the 3-point function exactly as we did for the conformal case. This is a scaling factor that takes care of the scaling transformation. And then this just contains the structures which we made in the superconformal invariant structure that we made. Okay. For example, let's consider a spin 1, spin 0 superconformal correlator. These are all the structures that we can have, which are built out of the invariants that we have constructed. Right? So as you can clearly see, first of all, that just using this superconformal symmetry has restricted the number of structures which are possible for this correlator. Okay. Now, on top of this, I have two spin 1 superfield operators, identical operators, which means I have a permutation symmetry in them as well. So I can use that. So the even ones, actually all of them respect that. The odd, actually only one structure respects that, which is a linear combination of these last two ones. And hence what I can have is this correlator is fixed up to 5 even coefficients and 1 odd parity odd coefficient. So this is what superconformal symmetry has fixed this 3-point correlator up to. And now again, we can do this analysis, and we have done this analysis for as many correlation functions as you want and to whatever spin you want. And you'll have the number of structures that the superconformal symmetry constrains this correlator to. Okay. And on top of that, we can also try and see what happens when we have supercurrents in the correlator. And so we apply the shortening condition or the conservation condition, again using the lambdas as well. And so this is what we get. So let's say I consider the 3-point correlator that I considered, and so this was the form that I had written down. Now I impose conservation on the spin 1 currents or the spin 1 operators, making them supercurrents. And this is what the relations are that I get. Okay, it tells me that A2, A3, A4, and A5, all of these are related to A1, which means this kind of a correlator, a spin 1 supercurrent, and a spin 0 superfield general operator, it's fixed up to a single coefficient. The parity odd part drops out, and it's fixed up to a total overall coefficient, and in terms of the dimensions of this scalar superfield operators. And again, you can do this for any correlator, and you just have to apply the conservation condition, and this fixes the correlator up to a very few. There's also a counting that tells you what happens when you have conserved correlators, 3-point correlators, and so yeah. So this is what basically the work was, figuring out the conformal invariants or superconformal invariants and writing 3-point correlators using them. So that is basically it. So 3-point superconformal invariants. So we did this work. So we did this analysis in 3D as well, and we saw that in 4D the methods are really trickier, and the invariants that we get, the structures are a little bit more trickier because of the SL2C Lorentz symmetry. While in 3D we get an SL2R Lorentz symmetry, and inversion actually implies, conformal symmetry implies inversion. In this case, conformal symmetry does not imply inversion, while the other hand is true in 4D, which is what makes the construction of superconformal invariants in 4D a little more difficult. Now, a general 3-point correlator is for any spin is easily obtainable through the method. Conserved correlators require a little more computational expense because you have to apply the differential operator on each correlator. And also we looked at some correlators where we have a mix of conserved and non-conserved operators, superfield operators. So this was basically the summary of the work, and currently we are looking at generalization of this thing to arbitrary Lorentz representation, not just stopping ourselves at symmetric traceless, So looking at chiral primaries or anti-chiral primaries as well. So I comma 0 or 0 comma j representations as well. It would be also interesting to extend this to an extended SCFTs in 4D, and a general counting for SCFT 3-point functions or superconformal correlators is still missing in the literature. Accounting is there for conserved supercurrent correlators, but not for a general superfield 3-point correlator. And one could also look at implications of weakly broken higher spin symmetry. So if we have, we're looking at exactly conserved higher spin symmetry when we're conserving everything for higher spin operators. And we're also looking at extending this formalism to CFTs where we have a more restricted symmetry. For example, non-relativistic CFTs where we have Schrodinger symmetry and so on. So yeah, that was basically the work that we did. And thank you so much. I'll be happy to take some questions. Thank you. Yes.
Didn't follow the full formalism, but I had some general questions.
Right.
So it was, first of all, you had this, in 3D, you have this result by, like Maldason and Zibida, which says that 3D exact high spin symmetry
Yes.
is basically trivial.
In the conformal case,
In
yes.
the conformal case. So do you know whether that has been generalized to 4D?
I think yes, it is.
So
And
I'm
in
just
4D,
asking about conformal.
yes. In the conformal case, I think it has been generalized to 4Ds as well. And you, I think, get three structures. You have a free vector, free boson, and a free fermion structure.
And the earlier part of the talk, when you're talking about the conformal invariance, that method can be used to show this. Have you checked that? The classification.
Yes, you can show this. You can actually show this. So
Okay.
if you go to higher spins, you'll find that the number of structures is exactly the same for the conserved correlators only.
Yeah, conserved correlators only. Okay,
Yeah.
but those are determined to be these vectors and free
Yes.
theory correlators. Okay.
Again, for a super conformal case, that restriction is still not completely understood. So because we don't have a unique stress energy tensor, and for supersymmetric theories we have in the 3/2 multiplet we have a stress energy tensor, and the spin 2 multiplet we have another stress energy tensor. So we don't have an exactly a unique stress energy tensor, which is what makes this a little hard to understand in the higher spin part.
But you can just understand. You can just choose one multiplet, right? Does it matter which multiplet you choose?
I think it does, because I think that's what the literature says, that because we don't have a unique.
Okay, maybe like what I would have expected is something like this. That let's say, let's talk about, let's say n equal to 1.
4D.
4D. N
Sure,
equal to 1
sure.
4D super. So then like you might want a result like the 3-point function is a linear combination of some chiral multiplet plus some vector multiplet and something. And then I would think that, okay, if you choose to use 3/2 multiplet, then is a 3/2 multiplet of the chiral thing, and 3/2 multiplet of the like vector multiplet and so on and so forth. And if you use other multiplet, you'll get the other one. But this basis statement is somehow should be independent of what multiplet you use. This is what I would have expected. You are saying that's not true?
I don't think so, because if you look at the 3-point correlator, okay, even our analysis suggests that again, this was something that Raghu and we were talking yesterday with Rajesh as well. Even if we have this kind of a thing, right? The Grassmann structure, let's say this structure A4, is not independently killed if I remove the bosonic structure or the superconformal primary structure, which means that it's not, so the Grassmann even structure or any Grassmann structure in the correlator, in the superconformal correlator, is not exactly generated or known using just the superconformal primary, the highest weight state of it. So I'm not sure if the stress energy tensor that you have in the primary case is the same as you would have in a descendant kind of a case. Does that make sense, or does that not?
Yeah, that I agree, but okay, what I'm trying to say
Hmm.
is that these coefficients are similar if you're using the same multiplets. Um, Maybe I'm not being very clear.
These
See,
coefficients.
let's kind of fix it
Sure.
that we will always use the spin 2.
Spin 2, okay.
Okay, we start with stress tensor and then descent.
Sure.
And I do that in the for the free chiral multiplet,
Sure.
free vector multiplet, all these things. And then I calculate the 3-point function also using that spin 2 multiplet only.
Okay.
Then I want to write the general thing as some linear combination of these things
Right.
with some numbers.
Right.
Okay, so I got some numbers.
Right.
Okay. Now what I'm trying to say is that, okay, so now let's say we go back and start with the other way of writing the stress tensor multiplet, where
Right.
you start with the current,
Okay. I think I
the
get.
supercurrent.
Right.
Okay. Okay. Then I would think the same numbers you'll get if you use the supercurrent multiplet everywhere.
Hmm.
This is what I'm trying to say. I'm
I-
not sure I'm being very clear, but
No, now I understand now. I don't
the
think
numbers won't change provided you use the same multiplets on everywhere.
I don't think that's the case. Again,
don't
it's a
think that's
little unclear in the literature as well. This high spin symmetry, and does it give you a completely fixed free theory or not, is also a little bit unclear in the literature for the superconformal case, of course.
Okay.
In 3D and in 4D, not just like in 4D.
Okay.
But yeah, very good question, very pertinent. This is something that we are currently looking at as well, trying to understand this.
Are there any questions online? No, there. Any one of you have any questions? Okay, so let's thank the speaker again.
Thank you so much. Thank you so much, Raghav. Thank you for attending.
You're going back to my phone.
No, I'll be around.
Yeah. Backward.
Yeah.